in order for us to use the proofs by induction on something else, we need to introduce a notion of divisibility that is pretty straightforward given general average human's acquaintance with numbers. So I'm going to start with two integers, n and d cannot be 0. N is the thing we're going to be dividing, and d is what we're going to be dividing it by. So we say that d divides n, or n is divisible by d, if and only if we can write n as d times some other integer k. In which case too, because we would like to avoid saying so many words, we use symbols in mathematics to be efficient, we would write d vertical bar n. So we read it as d divides n. Let's try out a couple of examples just to see how this actually works with numbers to solidify our understanding of the definition. So for example, 3 divides 6. This seems like a pretty obvious statement, except for when we start dealing with bigger numbers, we will have to be comfortable with what exactly that means. 3 divides 6 because 6 is equal to 3 times some integer, in this case 2. This is what this definition is saying. 3 divides 6, if and only if I can write 6 as 3 times something else. I also am allowed to use negative numbers because notice that we are within integers, so positive and negative are both allowed. So I can say something like, for example, minus 4 divides 80. And that is because 80 is equal to negative 4 times negative 20. All of the numbers here are allowed to be, in fact, negative, but they must be integers. We're not allowed to have fractions. If we have something that does not divide another number, we will have the vertical bar with a little dash through. So some books put it sideways, some books put it through perpendicularly, it doesn't really matter. So for example, 15 does not divide, let's say 13. And that is because there is no integer k such that 13 is equal to 5 times k. Because the numbers are so small, we can easily check that this is in fact the case. Now, another notation that we're going to use throughout is the one that corresponds to even and odd numbers. Even numbers are the numbers that are divisible by 2, which means that they're the ones that are written as n equals 2k for some integer k. The odd numbers are the ones that are exactly not divisible by 2. So if I divide an odd number by 2, I will have a remainder of 1. So the odd numbers are written as 2k plus 1 or 2k minus 1. It doesn't really matter for some integer k. So for even numbers, I have to be able to write it as 2 times something, so a product of 2 and another integer. And odd numbers, I have 2 times some integer plus or minus the 1. All right, so now let's see how we can use our definitions of divisibility in order to prove some divisibility properties. We're going to use induction here, and that is usually obvious from the fact that the statement concerns all numbers that are greater or equal to some number. So in this case, it says that n belongs to natural numbers. So recall that natural numbers are our counting numbers. So everything from 1 to everything we can count with, all the way into infinity. So 5n minus 1 is divisible by 4 is going to be our statement p of n. And in our basis step, as last time, we're going to choose the smallest number to use and see if that works. So if n is equal to 1, what do we have? We have 5 to the power 1 minus 1 is divisible by 4. Is that true or not? Well, 5 to the power 1 minus 1 is 5 minus 1, which is 4, which is divisible by 4 because I can write 4 as 4 times 1. So we're good to go here. So this is correct, which means that P of 1 is true, and we have checked our basis step. For the inductive hypothesis, as before, we're going to assume that P of k is true for some k greater or equal than 1. And again, we're going to write it out explicitly because I would like to be able to refer it in the current context. So that means that 5k minus 1 is divisible by 4. And let's write it out using this notation of multiples, because the divisibility itself is only useful more or less verbally, but the algebraic relation is given to us by these equations that we create out of the statement of divisibility. 5k minus 1 is divisible by 4 means that there exists some number, because k is already taken, let's use number, I don't know, m, so that 5k minus 1 is 4 times that m. So here, let's say for some integer m. So this is our inductive hypothesis. We have this relation between our number and 4. We need to prove that p of k plus 1 is true, which in our divisibility language means I need to prove that 5, now remember n is replaced by k plus 1, so 5 to power k plus 1 minus 1 is divisible by 4, which means in our language of equations, I need to be able to write 5 to power k plus 1 minus 1 as 4 times something. Now notice that this something isn't going to be the same exact number. It's going to be some integer m. It exists out there somewhere in the world, and we don't quite know yet what the relationship to this m is, so let's call it something else, like s. So for some integer s. And this is the thing that I need to prove. So let's start with the left-hand side here. I have 5 to power k plus 1 minus 1. What are my ways to proceed? One thing I can do is, well, one thing I really should be doing is looking back at my inductive hypothesis to see what are the types of things I am able to utilize. So here I notice that I will be able to utilize something if I have it in the form 5 to power k minus 1. So not quite 5 to power k plus 1. So I should be trying to reduce the power of 5 in order to be able to apply inductive hypothesis. So let's see. One thing I can do is I can rewrite 5 to power k plus 1 as 5 times 5 to power k. Remember that the powers add to each other if you multiply the same base. So this is the one thing I can do. So now let's see here. I have this expression now. I would be able to use it if I had 5k minus 1. I don't have it quite because this is not within the same brackets. But the other thing I can do is sort of like a little bit of rough work on the side here. Let me take this equation and instead rewrite it for 5 to power k. So let me move this minus 1 over to the right. So what I'm going to get then is 5 to power k is equal to 4m plus 1. And that is something I can plug in for 5 to power k here. So this is going to be 4m plus 1 minus 1. And as always, remember that I have to justify the usage of inductive hypothesis so that it's very clear why am I able to continue writing equality here. Now, let's expand out this expression. Remember that I'm trying to write this 5 to power k plus 1 minus 1 as 4 times something. So here, I don't have the 4 times something yet. Let me open up the brackets. So what I have is 40m plus 5 minus 1, or 4020m plus 4. And now I can actually factor 4 out. So what I will have left in the brackets is 5m plus 1. Now, remember that m is an integer. If I take an integer and I multiply it by 5, it's still going to be an integer. And if I add 1 to it, it's still going to be an integer. So what I can do at this step is just to rename it into s, which will be an integer. And so overall, here I have 4s. And I'm done. I have started with the expression 5 to power k plus 1 minus 1, and I ended with a multiple of 4. We're good to go here. This is one way of approaching this proof. I'm going to show you 3 different approaches, and you can decide for yourself which one you prefer better. For the approach number 2, all I'm trying to do again is just prove this expression. So let's start with the left-hand side again. 5 to power k plus 1 minus 1. And in fact, my next step is going to be exactly the same. I'm going to separate one of the 5's out. So here we go. But now, instead of using the inductive hypothesis on 5 to power k, I'm going to do something a little bit sneakier. I'm going to change this 5. So instead of the 5, I'm going to write 4 plus 1. We all agree that 5 is equal to 4 plus 1, right? Good. So I'm going to replace 5 with 4 plus 1 and leave the rest of the expression as is. And now I'm actually just going to open these brackets. I know this seems a little odd, but let's see how it works out. So I'm going to have 4 times 5 to power k plus 5 to power k minus 1. And now it's clear why I bothered with this. It's because now I have 5k minus 1 separately. So I can apply the inductive hypothesis directly onto this expression. So by inductive hypothesis, I can simplify that. So I'm going to leave my first part as is, but this will now become 4 times m. And remember, my goal is to write the whole thing as 4 times an integer. And I can see that at this point, I can factor 4 out. So it's going to have 4, and then I'm going to have 5 to power k plus m. Notice, of course, that if m is an integer and k is an integer, 5k plus m is also an integer. So as before, I can simply relabel that as s. And my last step will be simply rewriting this whole thing as 4 times s. And I am done with my second way of proving this exact same thing. Now, if you didn't think that 2 ways was enough, I'm going to show you a third approach altogether. It's going to actually have a similar flavor to this one with the expanding of the integers itself. So let's see. I have no choice but to start with the left-hand side here, really. Or, I mean, there are possibly lots of other choices, but I'm going to start with the left-hand side here. And before I do anything else, what I'm going to do at this point here is I'm going to add a 5 and subtract a 5. Okay, and then what I'm going to do is I'm going to group together this 5 to power k plus 1 and this minus 5. Okay, I'm going to put them together in, let's say, a bracket, and I'm going to leave the other 2 things together. So minus 1 plus 5, I'm actually going to combine the 2. It's altogether going to give me plus 4. Now that I have this, I'm going to take 5 out of this bracket. So if I factor out 5, what I'm going to have left is 5 to power k minus 1. And now it's clear why I had to bother, because this is exactly the thing that I can apply my inductive hypothesis onto. So by inductive hypothesis, I can replace this expression with 4 times m plus 4. And now you actually notice that this case kind of directly corresponds to the first case, except for I got there via a different route. So I can factor out 4. What I'm going to have left is 5m plus 1. And as we've already seen, I can replace that with an integer called s, and altogether get 4s. Whichever way you prefer to go, whether you prefer to separate the 5 out first and then apply the inductive hypothesis after massaging it a little bit, or you prefer to factor out 5 first and then split that 5 apart, or you prefer to do some massaging of the entire expression to begin with, your final answer should be 4 times another integer. If that is the case, which is exactly what we were set out to prove, then by the principle of mathematical induction, we have proven that our statement holds for all natural numbers n. Let's check out this next induction proof, and you will notice that the divisibility proofs also have a certain structure to them that will appear in all of the induction proofs for them. So here we have for any integer n greater or equal than 1, we're supposed to prove that 3n minus 2 is odd. So this is going to be our proposition P of n. And you notice that my first base case involves n equals 1, so let's plug that in. What do we have? We have that for n equals 1, 3 to the power 1 minus 2 is odd. Is that true? Well, 3 to the power 1 is just 3. 3 minus 2 is 1. 1 is in fact odd, which means that this checks out. So P of 1 is true, and our base case is checked. Inductive hypothesis. For inductive hypothesis, we're going to assume that P of k, so 3k minus 2 is odd, for some k that is greater or equal than our base case. Now, this is why we wrote out on the previous page what odd means. So if we flip back, remember that odd numbers can be written as 2 times something plus 1 or 2 times something minus 1. It really doesn't matter whether it's plus or minus 1. Pick whichever one you prefer. So what this is saying is that I can write 3k minus 2 as 2 times some number, let's say plus 1, where m is an integer. Okay, we can't use k anymore here because we've taken up that name for the variable in the inductive hypothesis. Excellent. What is it that we need to prove? We need to prove that 3k plus 1 minus 2 is odd. And again, writing that out in the format of an equation, what that means I am after is that 3k plus 1 minus 2 is equal to 2 times some integer, let's call it s, plus 1, where this s is an integer. All right, let's see what we can do here. I am going to start with the left-hand side, so 3 to the power of k plus 1 minus 2. And just like in the previous proof, what I'm trying to get to is somehow being able to use this expression of 3k minus 2, whereas I'm starting with 3 to the power of k plus 1. Remember in the last question, I showed you 3 different ways of doing this. Here, I'm only going to follow one, but I strongly encourage you to try the 2 others that are analogous to the question from the last page for yourself. So what I'm going to do is I am going to multiply 3 by 3 to the k. So I'm going to split up this 3 to the k plus 1 minus 2. And then I'm going to use the first way that I did on the last slide, which is to rewrite this equation in terms of 3k. So I am going to think about isolating this 3 to power k, which means moving this 2 over to the right-hand side. So here then I'm going to have 2m. Now notice that I'm going to have plus 1 and then plus 2, so altogether plus 3. All right, so now that means I can replace this 3 to power k by inductive hypothesis with the new expression. So instead of 3 to power k, I'm going to use 2m plus 3, and then altogether minus 2 that is remaining from the outside here. Excellent, let's open up these brackets. So what do I have? I have 6m plus 9 minus 2. So 6m plus 7. Remember, I would like to prove that it's odd, which means I can write it as 2 times something plus 1. So this 7 is going to be the one that contributes to the plus 1. So let me write it out as, instead of 7, I'm going to have 6 plus 1. And then, because I would like 2 times something, I'm going to factor 2 out from the first 2 terms here. So I can take 2 out from here. This will result in 3m plus 3, and then plus 1 will remain on the outside. And now I have the proper shape. I have 2 times something plus 1, 2 times something plus 1. So all that is left to do is relabel this something into s. The one argument you do have to make for yourself is to make sure that this s is in fact an integer. So notice that all the things that I've been using, m, 3 to power k, m is an integer. So if m is an integer, 3m is an integer, and 3m plus 3 is also an integer, which makes for an integer altogether. So what I have here now is 2s plus 1, and we have actually proven our assertion, which means that we've been able to, the principle of mathematical induction, now assume that Pn is true for all the cases above the base case. Okay, as I said, I followed the first route of the proof from the previous page. Try to follow through the exact same way, but using one of the other two ways. Next example involves using induction to prove an inequality. So let's see how that works out. We're asked to prove something for every integer greater or equal than 3. And that something is that 2n plus 1 is less than 2 to power n. So this is my statement Pn. So notice that my base case here has to be at least 3. So I'm going to try it out with 3. So what happens if I plug 3 in here for n? I'm going to get 2 times 3 plus 1 is less than 2 cubed. If I simplify this, what do I get? I'm going to get, let me just move it over here. I'm going to get 7 is less than 8, which is of course true, which means that my base case checks out. For inductive hypothesis, I'm going to assume that this is true. So 2k plus 1 is less than 2 to power k for some k that's greater or equal than my base case, which is 3. And I'm going to need to prove that this is true when n is replaced by k plus 1. So let's do a careful plugging in here. So I have to prove that 2n, which is replaced by k plus 1 is less than 2 to power k plus 1. Okay? Excellent. So what is my inductive step going to be? I'm going to start with the left-hand side here, as per usual, 2k plus 1 plus 1. I can, of course, open up the brackets. So I'm going to have 2k plus 2 plus 1. And notice that my inductive hypothesis includes 2k plus 1. So I'm interested in these two terms. Let's maybe move them together closer so I can see what the actual inductive hypothesis applies to. I'm going to leave these two out of the brackets altogether. So I can apply the inductive hypothesis to this portion, and by inductive hypothesis, this portion is less than 2 to power k, which means that if I substitute instead 2 to power k, I am not going to get equality anymore because this expression I know to be less than that. So now my equality actually turns into the less than sign. And the reason this appears is because of the inductive hypothesis being an inequality. Okay, so notice that while these things were equal, I'm now replacing it with a less than because I'm replacing this expression by something smaller than it. Okay, so now I have on the right-hand side 2 to power k plus 2. And remember, keeping our eye on the price here, this is the right-hand side that I'm interested in. So my next step, I'm going to make a bold statement that this is less than 2 times 2 to power k. I'm going to leave this as exercise to prove rigorously. Leave as exercise to the reader. Don't you love those? But it's actually reasonable to believe. What this is saying is if I have a quantity, adding a 2 to it is less than if I multiplied it by 2, right? Let's pick a quantity. Let's say it's, 5. Adding a 2 to 5 is not going to produce a number as big as multiplying the 5 by 2, right? So this is actually going to be true for all the numbers above 3. It's not going to be true for very small numbers, but in our case of k greater or equal than 3, it's actually going to be true. Again, I leave that as an exercise for you to double make sure. Now, once I am here though, I can put these two together, right? This is 2 to power 1 and 2 to power k. So altogether I have 2 to power k plus 1. And that is exactly the right-hand side here, which means that I am done with my proof. So by the principle of mathematical induction, P of n is true for all n above the base case, which in this case is greater or equal than 3. Let's now combine our skills to prove something about an inequality and also a factorial. So my interest here is this statement. For any integer greater or equal than 2, I would like to prove this particular inequality. The basis step is going to be at least 2, so let's start with 2 and see if it works. If I plug in 2, what do I have? I have 2 squared is less than 3 factorial. 2 squared is 4, 3 factorial is 6, so 4 is less than or equal than 6. This is true, P of true is true, and we are done with the base case. For the inductive hypothesis, I am going to assume that 2 to power k is less than k plus 1 factorial for some k that is an integer. And I'm not going to actually bother writing that. I'm just going to write down that it's greater or equal than 2. I need to prove, again, remember, I'm replacing n with k plus 1 here. So k plus 1 goes in here. K plus 1 goes in for n, which makes the factorial on the right-hand side equal to k plus 2 factorial. So I need to prove that 2 to power k plus 1 is less than k plus 2 factorial. All right, let's get to it. What do I have on the left-hand side? On the left-hand side, I have 2 to power k plus 1. My induction hypothesis involves 2 to power k. So one thing I can do is separate the 2 to power k from the 2 to power k plus 1. And now that I have 2 to power k, I can apply my induction hypothesis on it. So by induction hypothesis, this number is less than k plus 1 factorial. Okay? So now, similarly as in the example before, if I'm replacing this value with something smaller than that, what I'm going to end up with is going to be less than what I started with, right? So I'm going to have less than, and again, this is given by inductive hypothesis. So what I have altogether is 2 times, and then I'm replacing it with k plus 1 factorial. All right, well, this is sort of good news, but now I am going to have to look ahead as to what I'm trying to prove. And what I'm trying to get to is k plus 2 factorial. This is, again, where familiarity with factorials is going to be very useful. I have 2 times k plus 1 factorial. I would like to somehow turn it into k plus 2 factorial. So little work on the side here, because again, I know where I'm going and I know where I am. Little work on the side here. How about an observation? What I can observe is that 2 is less than k plus 2. The reason I can observe that is because if I actually move stuff around, I can move this 2 over to the left-hand side, minus 2. This will give me the fact that k is strictly bigger than 0. That's certainly true because in fact, k is greater or equal than 2, not just strictly greater than 0. It also cannot even be 1. Okay, so if k is bigger than 0, then k plus 2 is certainly bigger than 2, which means this 2 can get replaced with k plus 2. And the expression is only going to grow. Okay, so this 2 will get replaced by k plus 2. And then I'm going to leave my factorial be k plus 1 factorial. Okay, let me move this reasoning, let's say out here. I'm going to circle and point. All right. Now, why was this useful? Well, look what I have ended up with here. I have k plus 2, and then I have k plus 1 factorial. So k plus 1, k all the way down to 1. So notice that if I combine all of these together, these are all in a row from 1 all the way up to k plus 2, which means that all together, this is none other than k plus 2 factorial, which is precisely the thing that I was supposed to prove. Inequalities can be tricky because you have to make observations that are seemingly out of left field. But as long as you have your eye on where you're supposed to end up with, this will give you a direct hint as to what you're supposed to be using and what are you supposed to be trying to substitute in order to get from the left to the right-hand side. Now, because we've proved the actual inductive step, now we can say by the principle of mathematical induction, P of n is true for all the cases of n greater or equal than the basis step, which is 2. Next up, let's consider an example that contains a result that we've already proven, not using induction, but rather using a counting argument. We will now go through the induction proof of the exact same thing. A finite set with n elements has exactly 2 to power n subsets. So this entire statement is actually our P of n. The basis step, so it says n elements, therefore it can be anything from 0 and up, because we can have an empty set. The basis step, therefore, will be n equals 0. So if I have n equals 0, my finite set here is actually going to be an empty set. So now I just have to check whether or not it's true that it has 2 to the 0 subsets. So what do I have here? My result will claim that this has 2 to power 0 or 1 subsets. The empty set has only one subset, and that is itself. So this formula gives me 1, as it should, which means that P of 0 is true. The inductive hypothesis is we're going to assume that P of k is true, which means that in this case, we're going to assume that it's true that a set of k elements has 2 to power k subsets. And we need to prove that a set with k plus 1 elements has 2 to power k plus 1 subsets. So this is different from the previous examples because in this case we don't have some sort of equation or inequality where we have a left-hand side and a right-hand side. And we start with the left-hand side hoping that we will simplify it to be the right-hand side. Here we have a structure with a specific property, and that is the only thing that we can actually begin to and rely on. Now that means I can write out A, my set with k plus 1 elements, as A1, A2, A3, and so on, all the way up to AK plus 1. This is a set with k plus 1 elements. I hope we can agree. I've actually listed them, right? What I'm going to do now, because I have to apply a inductive hypothesis, I need to find a set of k elements. So if this is my A, so let A be this, then what I'm going to do is consider set B that has the elements A1, A2, all the way up to AK. Now, the size of set B is k elements, which means I can apply the inductive hypothesis to it. So there are k elements in the set B. So by inductive hypothesis, this satisfies this property, which means I can assume that it has 2 to power k subsets. B has 2 to power k subsets. Now remember what subsets are. If this is my set A, and I have a set B inside of it, which I know is smaller because there's this element AK plus 1 out here, I can clearly see that every subset of B is also a subset of A because it lies completely within it. And that is an important observation. So first of all, each subset of B is also a subset of A. So that means I've now accounted for 2 to power k of the subsets of A. Now, all of these subsets that lie entirely in B do not include this element that belongs to A and not B. So the other types of subsets that I have to include this element as well. What I'm going to do is I'm going to take each subset of B and add a k plus 1 to it. So for each of these subsets, I'm going to add a k plus 1 to those subsets. Okay, so the way that I'm going to form it is I'm going to consider a subset of B and also include an element AK plus 1 in it. This will form a subset of A. Because there are 2 to power k subsets within B, I'm going to add this element to each one of those subsets. I will produce 2 to the k subsets more of that type, right? So if I do this, this results in 2 to power k more subsets of A. And this is in fact reminiscent of the counting argument we did, right? For each element of the set A, when you're forming a subset, for each of those elements, it's either in the subset or it's out. It's either in the subset or it's out. So now we're just focusing in on one of them and making that argument a little bit more generally. So I have 2 to the k subsets of A that are formed by simply being inside B, and I have 2 to the k more subsets of A formed by also including the element A sub k plus 1, which means that altogether, I have 2 to power k plus 2 to power k subsets of A. And how can I simplify that? Well, look, it's an apple plus another apple, which makes for 2 apples. So it's 2 of 2 to power k. And if I put them together using the exponential laws, that's 2 to power k plus 1 subsets. Now that is exactly what I've actually set out to prove, which means that by the principle of mathematical induction, my original statement P sub n holds for all n values greater or equal than the base case, which was in fact 0. This is just one example of how powerful induction is. As long as you can take a statement, reduce it by 1, and then work your argument back up, you will be able to prove something quite significant by induction. Now, what we have been using so far is the so-called regular induction, which has a strong version that will assume something more demanding and will proceed, though, through the proof in the exact same way. Most of the time, we don't need strong induction, and therefore we use just the regular type. But for those cases when one might need it, here is how we can formulate it. First of all, I'm actually just going to paste out the statement for the induction, for the regular induction that we used before. So let's just recall what it looks like. I just copied it from a few pages back. So we have that P of n is a statement for some integer n greater or equal than something. Let me just erase the plus 1 because we've since then seen various iterations of what n can be. Principle of math induction states that you have 2 steps. The basis step assumes that the statement is true for some value n naught, and the inductive step is the following. It has a hypothesis. We assume that pk is true for some k above the base case, and then we prove the conclusion that the next case, the k plus first case, is also true. If we're able to do this, then P of n is true for all n above the base case. The strong version of induction is going to be very similar. So instead, I am going to replace not principle of math induction, but strong principle of math induction over here. And I'm going to change it actually very little. The base case will remain the same. We always have to make sure that we can follow the first domino. But the inductive hypothesis will actually change. Nothing else will change but the inductive hypothesis. Instead of assuming that only P of k is true, we're going to assume something stronger. So let me move this out a little bit. What we're going to assume is that every single thing between the base case and pk is true. So I'm going to assume that P of n naught and P of n naught plus 1 and all the way up to pk is true. So I'm not just going from one domino to the next. I'm assuming that every single domino before that fell, and I have to prove that that implies that the k plus first one will fall as well. So it's a stronger assumption because I'm not just going one step to the next, I'm going all the previous steps to the next one. And that is important for cases where just going one step back, so for example, in this example here, right, like we're We were trying to prove something about a set with k plus 1 elements, and the inductive hypothesis allowed us to move down to a set with k elements. In the strong version of the induction, we are going to be moving from k plus 1 down to anything from 0, the base case, so 0, 1, 2, all the way up to k. We would have had to make that assumption, and then when we call on it, we might not use just k, but maybe the set of size k minus 1, or a set of size k minus 3, or whatever we need. Let's see the principle of strong induction in action. So here is my example. Every positive integer above 2, greater or equal than 2, so it could be 2, is either a prime or can be written as a product of primes. Remember that a prime is a number that is divisible only by 1 and itself. So my property here is that any number is either a prime or can be written as a product of primes. And my base case is going to be n equals 2, as given to us here. So if n is 2, is it the case that this number is prime or can be written as product of primes? Well, this number in particular, it's prime. So since this is one of the allowable options, my p sub 2 is true, and my base case checks out. Notice that we're actually using logic rules that we've introduced before already. Or means that either it can be prime or a product of primes. Here, once I've determined it's a prime, I can move on because it's by default true. This, as a part of the inductive hypothesis, includes ands, which means every single one of these must be true because that's the only time that the entire conjunction is true. So my inductive hypothesis is going to assume that all the numbers up until a certain number k can be either primes or written as a product of primes. So here I'm going to set let k be greater or equal than 2, my base case, such that p of 2 and p of 3 and p of anything between the base case, which is 2, and my k is true. And let's write out what that means in our case. So all integers up to k, not just k itself, but all the integers up to k are either prime or can be written as a product of primes or a product of primes. Okay, so that's the main difference. In the regular induction hypothesis, I would hypothesize something about k. In the strong induction, I'm hypothesizing something about all the integers that came between the base case and k itself. And we're going to need to prove the same statement as before, that our statement here is true for k plus 1. So we're assuming that k plus 1 as a number is prime or is a product of primes. Okay, so what do we have to work with here? Again, this is not like an equation or an equality. We don't have a left-hand side that we have to show equals or is less than or something like that to the right-hand side. The only thing here we have is some kind of a object and a quality of an object that we're trying to prove. So what I have is just k plus 1. That's literally the only thing I have here. K plus 1. What I'm trying to prove is that it's either prime or, in case it's not, it's a product of primes. So I actually have two cases. First of all, k plus 1 could just be prime. So if k plus 1 is prime, then we're done. Because, as you remember from logic rules, if one part of the disjunction is true, then the whole thing is true. We're done, and p, k plus 1, is true. So this is the case when it's prime. What happens if it's not prime? So if I have k plus 1 is not prime. Remember that primes are numbers that only have two divisors, 1 and themselves. If k is not prime, it means that k plus 1 can be written as a product of two numbers that are not 1 or itself. So let's just do a number example for just so that we can ground ourselves. 7 is a prime because the only numbers that divide 7 are 1 and 7. 8 is not a prime because it has other divisors. So for example, 8 can be written as 4 times 2, or 2 times 4, or 2 times 2 times 2, or something like that. But in any case, it can be written as a product of two things that are not just one in itself. So if k plus 1 is not prime, it can be written as a product of two other numbers. Now, whether or not they are prime, we don't know, but they are some numbers. Now, notice that because these numbers are not, so let's write this out, where x and y are not, and y are not 1 or k plus 1, right? That's what makes it not prime. They're actual numbers that factor out k plus 1. So that means because it's not k plus 1, this number, this x, is less than or equal to k. It could be equal to k, but it's certainly less than or equal than that because it cannot be as high as k plus 1. And same is true for y. This is less than or equal than k. It's not necessarily k, but it's something less than k. It's an integer that is smaller than k, which is fantastic news because our inductive hypothesis allows us to say something about any integer that is smaller than k. So in our next step, by inductive hypothesis, we can therefore say that x and y are each either prime or a product of primes. Now, if I take two numbers that are each either prime or a product of primes, that means that when I multiply them together, I'm going to get a product of primes. So, x times y is a product of primes. Now notice that it doesn't actually necessarily mean that like a product of primes could be something that looks like this, right? There could be more than one. So maybe this is my x and this is my y. So each x and y can be consisting of more than one prime. That's what it means for each of them to be more than a product of primes. But if I multiply them all together, I will have a product of primes happening. And that, of course, is exactly what I've been trying to prove. My first case covered the prime, my second case covered not prime, and therefore resulted in product of primes. But by both of those cases, what I have altogether is that by the strong principle of math induction, P of n is true for all n above my base case, which in this case is true. I just want to pause for a moment and say just how amazing this is. I took a structure, I assumed something was true for all integers up until a given one, and then I was able to use just very basic properties of numbers, such as divisibility and the size of the factors, to prove that every number is either prime or can be written as a product of primes. Notice that in this case, I really did need the strong induction. I couldn't have used the inductive hypothesis here if it was regular, because I couldn't say anything about the fact that if x was just equal to k, that wouldn't have been helpful. I really needed to have the assumption that worked for all integers up to k in order to be able to apply it as an inductive hypothesis. This is the strong induction. You notice that the steps are very similar to the ones before, but the way that we use the hypothesis is a little bit different.